Okay, the previous, we're talking about math modeling in a controlled systems course, and we covered a mechanical system, a simple mechanical system, mass spring damper. Now we'll cover a simple electrical system. And believe me, I'm only going to spend about 10 minutes on this, and it can be a whole course. So it's only going to be passive RLC circuits, meaning resistance, inductance, and capacitance. Passive elements only, except for some external forcing functions. And we just use Kirchhoff's laws, which are voltages in a loop sum to zero, and currents in a node sum to zero. So here is a loop around this E sub I through these inductor, resistance, capacitors around here. There aren't really nodes in this case. This kind of looks like a node, but it isn't really. This voltage drop to the right is really just the voltage drop across this capacitor. So we'll call little I the current, little e the voltage of any given element. When you analyze a diagram like this, you get to define what you mean as positive current. So imagine a loop of current going around here. I'll define positive as clockwise. You could define it as counterclockwise. Oops, I think I'm losing my Zoom, or at least the video of the Zoom. Okay, it's back. So we'll have a little I, call it clockwise here. And each of these elements has some kind of voltage drop. This is an external forcing function like a battery. You have to know, you have to be given what's positive for this force. So it's labeled as plus up here and minus down there. The voltage drop across these passive elements is opposite of the current through them. The voltage drop of this inductor is proportional to the time derivative of that current. Voltage drop across this resistance is just proportional to the current itself. And the voltage drop across this capacitor is proportional to the integral of the current. So let's use this Kirchhoff's voltage law. It says all the voltages in this loop must sum to zero. So this voltage, if I define this current clockwise, follows this plus. So this voltage is a plus. This voltage drop will be a minus. And remember, it's proportional to the time derivative of current. This is also a minus. And the resistance voltage drop across the resistor is proportional to the current itself. And this capacitor, if we define the voltage drop as plus on top, is going to be minus the, well, it's proportional to the integral of the current and its opposite direction of the current. And we need a definite integral here, and we're going to assume the current is, or the voltage initially before you start at time t equals 0 was 0, okay? So that Kirchhoff's law says you get this math model or this differential equation using Kirchhoff's voltage law. And then the voltage drop across the capacitor is just the voltage drop across the capacitor. See, well, here's what we just had from the previous chart. If I now define X as this current and take one more derivative of this equation, I'll have an E sub I dot, its derivative, minus L times X double dot, because I'm taking another derivative, minus X dot times R, minus just X, because I took a time derivative. If you look at that, this is just a second order differential equation with this external forcing function. It's mathematically equivalent to the mass spring damper system. We'll look at a multi-loop example, and I don't want to get too deeply into it, but in this case, you look like, there's a loop there and a loop there. There's two loops. Actually, there's the whole big loop around the whole outside. But of those three loops, I hope I didn't lose my zoom again. There, it's back. One of those loops is redundant. Sometimes that makes the analysis kind of tedious. You might have to do some trial and error if it's a very complicated case. But this is a case of two non-redundant loops. And you're going to have a differential equation for each non-redundant loop. Just like we had a differential equation for each mass in a mass spring damper system with multiple bodies of masses. You can have multiple differential equations with a multi-loop electrical circuit. So these little currents are something you, the analyst, would come up with. You get to define what you mean by positive. So I'll say there's a current around here, positive clockwise, and a current around here, positive clockwise. And here we need to use Kirchhoff's node law. Up through here, I have this I sub 1 that goes into this node. Then coming out of that node is this I sub 2. So if I want to know what the current down through this path is, I need to use Kirchhoff's node law. These currents need to add like this. If I define these two guys positive and this one is downward positive, they need to add to 0 this way. So this I sub 3, I'll call it, which is positive down through this branch, is this I1 minus this I2. And now I can do each node separately. This little external voltage source, I'm going to have minus this R times I, minus this L1, the derivative of that current, plus this capacitor. And this notation means the flat part is the plus side, the curved part is the minus side. And that's I3 through there, which I can express using the I1 and I2. And then this R, same kind of thing. This is the equation for this loop. And this will be the equation for this loop. I'll have, what is it? Okay, this capacitor, this inductor, this R, and this C. I have 4 different voltage drops around this loop. We got to be careful with signs again. So two differential equations for the 2 non-redundant loops. This can get confusing, I know, and I'm covering it very quickly. But there's some big ideas out of this. You saw that we get similar differential equations for both electrical and mechanical systems. And we could do other systems. Linear motion, rotational motion, heat flow, fluid flow. I can direct you to my signals and systems course, which is a little bit more extensive treatment of these things and how to model them in a more rigorous, methodical way. But they all end up as differential equations. So by studying those differential equations, we're studying the dynamic behavior of physical systems. We can also study how to control those systems by analyzing those differential equations. So if the rest of this course looks a little bit too mathy for your taste, that's the way it is. But here's the connection to the real world. These differential equations come from physical systems, or at least they adequately model physical systems, at least in certain situations. And that's the big idea. And that's all I'm going to talk about math modeling. Again, sometimes this is an entire course, prerequisite course for controls. It was a more, when I taught signals and systems, which was a prerequisite for control systems course at one of the universities I taught at. It was covered a little bit more extensively. So depending on how deep you want to get into it, you need to look elsewhere, like my signals and systems